Thank you, Matt. Please, everyone, keep your hands up. Brian, I saw your hand first, so you start. Other people, keep your hands up on the list.
My question is similar to some things that were being said by Raphael Sorkin and others about the definition of time symmetry. I'm thinking about the example of classical mechanics in which if I'm thinking about just free particle, that typically when this is a totally time-symmetric theory, but typically when I take a trajectory of a free particle and I time reverse it, I get something that's not the same as the original trajectory. It's very hard to find such trajectories. They're just the ones where you just sit there without any velocity at all. The ones that where the trajectory is preserved. So in the case of quantum theory, so now there's no dynamics in the sense of a Hamiltonian. We're just looking at the probability. You might have said there's some natural notion of time reversal to transformation. We want to say what it means for now the system to be symmetric under this transformation. I might have just said, well, whatever the time reversal transformation does to my density matrices and to my POVMs, it takes the density matrices to some other density matrices, and it takes the POVM to some other POVM, and I need not ask that the probabilities be the same for those. It seems to me that when one asks more than just that they're taken to some other density matrices and to some other POVMs, and in particular you're asking that the probabilities be the same, that seems like, it seems analogous to asking that the trajectory in the classical system be the same under time reversal. And at least, I understand it's not like a perfect analogy, but I'd like to understand a bit better about why we're asking that the probabilities be the same under the time reversal transformation, even in the characterization. Before we even got to the ontological models, we were just looking at the operational setup.
So I'm not sure I quite buy this analogy that it's like asking for the trajectories to be the same. But I think there certainly is a worry about why exactly are you demanding that the probabilities are the same. And I guess I'm kind of taking a very naive kind of frequentist view of what the probabilities mean. They just mean that I've got a million videos and various different things occur with various different relative frequencies in those videos. And now I just run that entire collection of videos backwards. Well, then the relative frequencies are going to be the same, right? That's not something that's changed by whether you run a video forwards or backwards.
But if I put it in the language of instruments, isn't it a different instrument that is required to send them backwards? Like if they're going to the right in the forward direction, now they're going to the left. So then take a different instrument.
Yeah, so there is probably, I've been kind of a bit sloppy in some of the notation. There probably should have been lots of things that kind of show that the thing when you run it in the forwards direction, it doesn't actually have to be the same thing when you run it in the backwards direction. It has to be like a corresponding thing in the backwards direction. That would apply to the thing in quantum theory and to the ontological model. But my hope would be that that's not really essential for this argument. But we just think about that more.
Sorry, I've got a list of 5 hands at this point. We've got under 10 minutes left, so I'm not going to accept any fingers. Dustin, what do you know?
Why did you say that? Bony mechanics is time-symmetric, it's not retrocausal, and it's psiotic. So I don't think what you proved is wrong. I think your definitions are questionable.
Sure, yeah. So I would say Bowman mechanics violates something that I've been assuming implicitly, which is that the time reverse of a preparation is something like a measurement, and the time reverse of a measurement is something like a preparation.
Yeah, I have to think about that. But the equations are time reverses.
Sure, yeah. But if you just kind of think about it in in this simple case, then what would happen here in Bowman mechanics is that some of the wave function would come out here, some of it would come out here, particle would probably come out one way or the other. But that's not the time reverse of putting a photon in here or putting a photon in here. So I guess what was being called the discreteness assumption in this argument is something that I've just kind of implicitly made in the whole idea that preparation and measurement are time reverse of each other. So yeah, that was one of the important things that has been swept under the carpet. Thanks.
Hello.
I have a comment on the question. First, you have some citations which Van Tabe and then ABL, and I think Van Tabe should be taken out because it's not the time-symmetric story. Second question, in this example, then later you kind of replace tau by some qubits or something, and it looked for me like two-state vector. And if you look on a two-state vector like Aharonov final wave function, and if you say enlarge the ontic description is just not just one wave function but two wave function, this seems to me symmetric. And it seems looked like that you did something similar, but maybe I misunderstood you.
So I agree that the forwards and backwards wave function looks time asymmetric. But if I just tried to put it straight into the ontological models framework,
the question was ontological. If you say that the ontology are these two-state vectors. Right.
If I said that, then I'd run into the problem that the retrocausality is just ruled out by the framework. Okay. Because if I just said that the real state is the forwards evolving wave function, the backwards evolving wave function, well, the backwards evolving wave function depends on what measurement you do. Okay. And that kind of dependence is just not allowed in this ontological models framework. The model I gave is not like that. It's not that the quantum state going forwards is real and the quantum state going backwards is real. Neither of them are real. Okay. The forwards, this thing about them overlapping applies just as much to the backwards evolving wave function as it does to the forward evolving one.
James.
I think maybe you've been asked this and answered it, but I'll just try again. So it seemed like your underlying states here aren't affected by time reversal. There's no operation that you do to them that transforms them into something else. But in the normal, I mean, this is just what Brian was saying, I think, in the normal way of thinking about time symmetry, you're allowed to have an operation that transforms things into the time reversed equivalent, and then it's those things that are put together in a sequence that's supposed to be okay in the opposite direction. But your lambdas and your states don't seem to be changing. But were you saying that that was just something that you left out and you could make them change?
That was the claim, yeah. But yeah, it's a totally legitimate point. I can just think about it more.
Okay, thanks.
I mean, my assumption would be that at least there's a way of setting things up such that this argument gets through. But then, it's a question of how strong are the assumptions you're making about what exactly that time inversion operator does.
Yeah.
I suspect at the ontological level it would just have to be something like a bijection, but you'd have to think about it.
Ken.
Yeah, beautiful stuff, and I think you're right about the original argument. Do you think, though, that a version of the original argument might go through where instead of using the two settings, you use 0, pi over 8, and pi over 4, and use the Bell violations to do what the Speckham's toy model can't do, right? That get the cosine squared. Do you think that if you have three settings of the original argument, there might be some very convoluted proof that gets to the same point?
You don't even need three. So this, I should have made clearer that this is a proof of preparation contextuality for a single qubit, and you can think of it as being implemented using polarizing beam splitters, just like the original argument. Okay, so this is this is one setting, this is the other setting of the second one, and this is one setting, and this is another setting of the original one. And so you were in the original argument, there is enough of quantum theory to make the argument without the scientific assumption.
Right.
It's just that the argument was made.
Right.
Abi,
Can you go back to the chart figure? I made something.
What's that?
CSAR. You're talking about one photon going through two polarizers, or?
Yes.
Oh. So does it go, do I understand that there is a source somewhere at the beginning, and then two detectors pass the other polarizer?
Yeah.
Okay. So then when you reflect them back, there is a detector which clicks, and then you force that detector to eject, to emit back the photon, right? Alright. You should have put two mirrors, not make any detection, and then you are sure to get your photon go back exactly to where it went. The moment you introduce a detector, then in the language of Bohmian mechanics, for example, then you lose part of the empty wave which was absorbed. So little wonder that you don't get time symmetry here.
Yeah, I mean, that's right, except that I think we really do need to have detection or something like it, because we're actually using the outcomes.
No, so then
in
you're
order to find the
introducing,
outcome.
no, then you're introducing the time symmetry by having detection. You
Yeah, I mean, I think that's
one
a-
source, two possible outcomes. Then you take out one outcome and say, wow, it doesn't go back to the source, I now have two sources. I would say that's very symmetric.
We can discuss this more. There definitely is a non-trivial assumption, and it's a contestable one, but I hope it's at least the same one that's entering into the original argument. I mean, we were really just trying to fix the scientific assumption of the argument rather than any of the other assumptions.
What you're showing here is interaction-free measurement. When the wall does not reflect your photon back, then the wall is also making a measurement. The part which did not reflect, did not absorb the photon. So then you will see the picture becoming much more symmetric. We can discuss it later.
okay, I'm afraid we're out of time. Apologies to those people who had fingers. Please join me in thanking that.